Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on equilibrium constant, of which I'll be doing properties of Kp. So I'll be talking about partial pressures of gases, what Kp is, why it's used, and I've decided to split this video into two parts because I think the video itself isn't actually too long, it's roughly like 20 minutes. But then when I add on the exam type questions at the end, that's another 20 minutes, and people kind of get the idea that the whole thing is like 40 minutes. Or so the whole content is 40 minutes when it's already just 20 minutes and I have another 20 minutes of questions at the end. So what I'm trying to do now is that I'll split this video into two. The part one will be me explaining the content, and then the part two will be me going through examples and how to answer those questions. So that's what I'm going to be doing. So this is going to be the part one. So yeah, so for talking about partial pressures of gases, what Kp is, of course, it's an equilibrium constant, so it follows the general principles of equilibrium constants, but it's more tailored toward partial pressure. It's slightly different, and it's its own. Well, technically, it's one topic, is its own unit, but yeah, I'll go. Let's just enough waffling. Let me go straight into it. So, partial pressure of gases. So if you have a mixture of gases, you can split the total pressure into the pressure of each individual gas. What I mean by this is that partial pressures, right? So say you have a 50-50 mix of water vapor and nitrogen gas at a pressure of 1 bar in a concealed vessel, right? You can then define this by splitting it into partial pressures of water vapor and nitrogen gas. So this would follow the ideal gas law because it states that every gas occupies the same volume under the same conditions. So no matter if we maintain the same conditions, they would occupy the same volume. Sorry, let me rephrase again. Every gas occupies the same volume under the same conditions. So as long as the conditions stay the same, they'll be maintaining the same volume. So that's one thing I have to keep in mind here. So all I'm doing is I'm representing the volume of the gases in their standard conditions as a ratio of the total amount of gas, the total volume of gases within that vessel. And I make that sound way more complicated than it really is. But if I look back at this example here, where you have, say I have a 50-50 mix of water vapor and nitrogen gas, we would say that the water vapor has a partial pressure of, say you have a 50-50 mix of water vapor and nitrogen gas at a pressure of 1 bar, then we would say that the water vapor has a partial pressure of 0.5 bar and the nitrogen gas has a partial pressure of 0.5 bar, right? That's all. We're just representing that partial pressure, the volume of gases as a partial pressure, as summary or a fraction. You can use ratio, fractions, or decimals are probably the best way that we represent them. A decimal in comparison to the entirety of gases in that vessel, if that makes any sense. Hopefully I didn't butcher that. But I'll use a different mixture, right? So if we have a 75-25 mixture of oxygen and argon at a pressure of 1 bar, we would say that the partial pressure of oxygen is 0.75 bar and partial pressure of argon is 0.25 bar. Hopefully this second example it makes it clear what I'm trying to say here. We're just representing this, the total volume of each gas as a fraction, as a ratio, as a decimal in comparison to the whole volume that's in that vessel, so long as they maintain the same standard conditions. So what is a mole fraction, right? So another way to think about this is using mole fractions. So I said before I can use decimals, which was part of the partial pressures, right? But we can also represent them as mole fractions. So another way to think about them is, so for example, if we have 3 moles of oxygen gas and 2 moles of nitrogen gas all in the same vessel, you can define the mole fraction of oxygen and nitrogen as you can just represent it as a mole fraction, right? So if we're representing here as a let me just go back here. We know that this is a ratio of 3:2. That means you have 5 parts in total, right? Therefore, the mole fraction of oxygen is 3 out of 5. And that's it. We have 5 moles of gas in total within this vessel. 3 of those moles are oxygen, two of them is nitrogen. So the mole fraction of oxygen is 3 out of 5, and the mole fraction of nitrogen is 2 out of 5, right? And now all of this information allows us to work out the partial pressure, right? So we can't just work out partial pressure, but there's actually a method of working out partial pressure, and we then use those partial pressures to help us work out the Kp. I'll go through what the equation is for working out Kp later on, and there is an equation, but to work out the values that we're going to put in to our Kp equation, kind of like with concentration, where we have to work out the concentration using concentration is equal to moles over volume, right? We have our own method for working out the partial pressures, and there's a reason why we use partial pressure when we're working out Kp in response to working out values for Kc. I'll go through that later. But coming back onto this, if you multiply the mole fractions that are here, right? Oh, don't use that. If we multiply the mole fractions of oxygen, so the mole fractions in general, by the total pressures, by the total pressure, you can then work out the pressure of the gases. So if you have the total pressure of gas within that vessel and you have the individual mole fractions, you can multiply your mole fraction by your total pressure to work out the partial pressure. In fact, you know what? I will make that is actually an equation that you actually need to know. It will come second hand to you. They won't ask. Actually, they actually, I have seen a question where they've asked for you to write that down, but I will put that. I'll put that here. I'll put that just. Oh. Here you go. Here. Partial pressure I'll represent by PP. Or, you know what, there's enough space to write the whole thing. Partial pressure of that gas in that sealed vessel on standard conditions is equal to the mole fraction that we worked out. Again, to work out the mole fraction, you need to use an ice table. Remember, this is an equilibrium constant, so you like the same way how you work out the values for the equilibrium moles for Kc. We still need to, by using an ice table, we still need to use an ice table for working out the mole fraction, and I'll get onto how to do that later. In fact, the actual working out the numerical values and working out how to actually answer a question, that'll be in the part 2 to this video. The part 1 that I'll be focusing on right now is just to do with understanding what the content is about, and then I'll go on to actually how to answer the questions in the part 2 of this video, or this 2-part series, I guess. So anyway, partial pressure is equal to mole fraction times by the total pressure that they will give you. And if they haven't given you that, they'll give you enough information to work out total pressure. And if you think to yourself, how the hell am I going to work out total pressure? Just remember this equation. Right? So they always give you enough information to make sure that you can answer the question. They can never do that by not giving you enough information or assuming things that you don't know enough information to assume yet. So if they're giving you this, if they're giving you or RT, or so they've given you the temperature, the volume, and enough information to work out the moles, you need to do another moles equal to mass over the MR. Moles is equal to CV, right? If they give you enough information to work out the value for N, or if they give you just N directly, right, then you can just change this, rearrange this equation. NRT P, so pressure is equal to nRT over V. There you go, right? And now you have that'd be enough information to work out your total pressure there. But yeah, but this all I'm trying to say is that they'll give you enough information to answer questions. I'm just showing you that this here Actually, that's a terrible thing to do. I'll just use this instead. This here is the basics fundamental to getting to understand how to answer partial pressure. Anyway, though, so I was going to make this video about this part one video about content. I'll go back to content. So what is Kp? So Kp is a special type of equilibrium constant that we use for reactions that are in the gas phase. Kp, right? So where Kc uses concentrations, Kp uses partial pressures. The two approaches are equivalent, but it's much easier to measure the partial pressure of a gas than the concentration of a gas. Remember what concentration is. Concentration is the amount of moles of a compound within a volume, right? Moles of a volume. And the volume of a gas is within an air, right? And so you can't, it's very difficult to, sorry, that's really disturbing. I'll kind of turn that down. Really sorry about that. I didn't want that to be disturbing this, but you know me. Anyway, yeah, what was we talking about? It's, remember, in a gas, the particles are freely moving around in air, and that air is the volume, right? That region of space is the volume. Volume is the 3D area. So it's much difficult to work out the concentration of those particles that are freely moving within that that space of air compared to just working out the partial pressure. The partial pressure is much easier to work out than working out the concentration of a gas that's within that volume of air. And so that's why we use Kp. It's much easier to work out. So how is Kp defined? So the equation for Kp is this. It's literally the same principle idea as Kc, where it's the Kc is the concentration of your products or your concentration of your reactants. But no, remember, we're not doing Kc here, we're doing Kp. But it's the partial pressure of your products over your partial pressure of your reactants. I say that again. Kp is equal to partial pressure of your products over your partial pressure of your reactants. And if you think about it like this, so if I had the reaction of lowercase a, so A plus B goes to form C plus D, right? C here would be, the capital C here would represent that's your partial pressure. Then actually technically, you see, that represents partial pressure. But remember, when we're doing equilibrium constants, with the power of this lowercase c here, the molar ratio, which is represented by the lowercase c here, that represents the power in this case. That will be represented as a power. So if you have 2 moles of C, it will be partial pressure of C squared. And you should understand that basic concept when you did equilibrium constant of concentration, or the Kc. Same principle here, but we're just not using concentration, we're using partial pressure. And again, as I said, I'll explain how to work out partial pressure in the part 2 of this video. But that's just so you know, that's the equation that you need to understand and know off by heart. Wouldn't be too difficult to remember anyway. Anyway, so the properties of Kp. So much like Kc, Kp has a set of properties that you need to know. So Le Chatelier, just like Kc, as I said, just like Kc, Le Chatelier. So Le Chatelier's principle applies to Kp as much as it does to any aqueous equilibria. In fact, Le Chatelier applies to all the equilibrium constants, as far as I'm aware. It's just that there's different equilibrium constants for different things. You'll find out later on in this topic, there's an equilibrium constant for acids, there's an equilibrium constant for water. There's different equilibrium constants, but they all follow the general trend of having a set of properties, and one of them is Le Chatelier. They all are affected by Le Chatelier. And Le Chatelier's principle applies to Kp as much as it does to any A equals equilibria. So if you increase the pressure, the system will decrease the pressure by favoring a reaction that removes moles of gas. If you increase the temperature, the system will decrease the temperature by favoring a reaction that's endothermic. So said here, if you increase the pressure, the reaction will favor the side with less moles of gas. Increasing the temperature, the system will decrease the temperature by favoring a reaction that's more endothermic to lower the temperature. So temperature, so just like Kc, Kp is an equilibrium constant that is temperature dependent, and it will have different values at different temperatures, right? So depending on the type of reaction that you have, it will, if you're having an exothermic reaction, if you increase the temperature, you're increasing the KP will be higher because you are, it would be, yeah, you would be. I have to think about this one very carefully. No, say if we want, if we're having exo, if we had, if the reaction that we want is exothermic, by lowering the temperature, we're forcing the exothermic reaction. Yes, to because it's Le Chatelier. We're forcing the exothermic reaction, so KP should increase. Go with your teacher with this one. I said, if I ever make a mistake, I would like a teacher to tell you the actual truth of it. But from what I understand of it, if a reaction that we want is exothermic, we would lower the temperature to favor the exothermic direction of the reaction, and KP would be higher because we're favoring that type of reaction was an exothermic reaction. We favor that type of reaction. So yeah, I said KP and KC will have different values at different types of temperatures, depending on that type of reaction. Catalysts only increase the rate of the reaction by providing an alternate reaction pathway with a lower activation energy, and they do not, keyword here, they do not alter the KP. They do not alter the equilibrium constant, or they don't alter the equilibrium at all. So they'll be changing having a catalyst will have no effect on KP. It increases the rate of the reaction, but it doesn't change the position of equilibrium. Only change factors like temperature and pressure, or constant, or can actually concentration. No, temperature and pressure would affect the KP. And I'll go through why pressure here, right? So changing pressure doesn't actually, no, temperature and concentration should affect KP. Yes. But changing pressure doesn't alter KP. And the reason for this is, no. I'm really messing this up now. I'm really sorry. The only thing that should be affecting KP really is temperature. Because I remember also answering a question. I remember going exam questions and it was asking me what effect does concentration have on KP? It has no effect. And what effect does pressure have on KP? It has no effect. And the reason why pressure, I'll give an example why pressure doesn't have any effect. Because changing pressure doesn't affect alter KP, right? And it's because equilibrium is reached when the forward and reverse reaction rates are equal. So when we're in dynamic equilibrium, the rate of the forward and backwards reaction are equal, and these rates are determined by the number of successful collisions per second, which is determined by temperature, activation energy, and how often the molecules collide with the right orientation. So if they're the same number of molecules on each side of the equation, then the change of pressure makes no difference to the position of equilibrium. Hopefully that makes sense, right? And that's it. That's it for this part of the video.